And hello, welcome. As we like to say in Singapore, Hosebo. Yeah, so I'll try, since this is a video by a Singaporean, I want to introduce some Singapore slang every now and then. Um, it's basically just a colloquial way of communicating. Uh, it's our uniquely Singapore, uh, local slang and language. Okay. Um, yeah, so we call it Singlish. So yeah, Hosebo is like, hey, what's up? Or how are you? You good? Yeah, so that kind of a thing. So I want to kind of introduce a bit of that colloquial Singapore culture to the world. I probably won't get to do this at work, so this is really, my own hobby kind of thing. Yeah, so yeah, what's up? Hosebo. Okay, so today we want to pick up where we left off. Like we talked about some of nuclear technology last time and how it was pivotal to many developments in the Cold War. So I guess to start, we have to start why nuclear technology was developed in the first place. And then we start talking about, maybe we can segue a little bit more into the physics and the reactors and so on and so forth. So we start in, let's see, let's start annotating. Where is this? Yeah, freehand line. Okay, start at the Manhattan Project. This is, I think, lecture 3, Manhattan Project. We start the Manhattan Project. This was in 1942, very shortly after the US was bombed by Japan, and it starts having it started having this is almost a year after 1941 Pearl Harbor. I'm not too sure on the dates here, but Manhattan Project definitely started in 1942. So what was the objective of the Manhattan Project? So US was at war with Germany and Japan, and the idea was to quickly get a bomb started so that they could beat the Germans to it. Okay, you would have seen this in many of the books and movies about Robert Oppenheimer. Okay, I did not personally watch the movie because there were some scenes I was uncomfortable with, a little bit of nudity scenes. So I just read the book, at least 3/4 of the book, and I mean, just some trivia. I found out Oppenheimer cooked nasi goreng. This is a Indonesian dish. Countries in Southeast Asia uh, loved it. But yeah, Oppenheimer cooked nasi goreng, eh? Yeah, this is my favorite trivia of the book. But anyway, this is some things. This is what stood out to me besides the nuclear tech stuff. There are lots of other interesting things that happened in the Manhattan Project, but let's just focus on the science. Okay, so the object or the 2 products or 3 products that came out of the Manhattan Project were the Trinity device. So we're just going to draw a tower here. Okay, and the Trinity device is this little ball thing here. Okay, Trinity. This is in New Mexico. And of course, we have 2 bombs. One called Little Boy and one called Fat Man. Okay, so I will draw it as such. Okay, so this is the Hiroshima bomb. And this is Nagasaki. So these 2 bombs helped to quickly end World War II, especially for the Asia Pacific region. Okay, lots of death, unfortunately, but it did help to prevent more war from going on, I think. Yeah, at least from a Singaporean perspective, it ended the Japanese occupation for us because the Imperial Japanese Army treated us very nasty, in a very nasty manner, but it ended our suffering, at least for the World War II. Um, but of course, I think today our relations with the Japanese are much better. I think the object is to forgive, forget, or rather just forgive what was done, yeah, so that we can like move on and cooperate. I think that is the spirit I want to like have moving forward. But anyway, Hiroshima and Nagasaki. Okay, Hiroshima was a bomb primarily using U-235. Nagasaki was a bomb primarily based on plutonium-239. Okay, so before we go into specifics of the bomb, okay, Trinity was also oops, sorry. Trinity was also a plutonium-239 bomb. So it was an implosion device. Okay, so these are very specially designed bombs. I have no idea how to do them anyway. Okay, um, especially the plutonium-239. There's a lot of advanced mathematics that goes into that. How to shape an explosion such that it compresses a sphere uniformly. Yeah, that's the idea. Right, so there's a lot of mystery surrounding all of these nuclear weaponry and nuclear reactors. So I want to start off with the basic physics. Okay, I'm not going to do any equation here. I'll just briefly go through concepts. Okay, I'm going to go through concepts with as little mathematics as possible. So concepts with as little mathematics as possible. Okay, we want to go into the physics first. Okay, and then this is what I want to go through. Now, of course, my colleagues would say, or friends I know would say, physics has to have math. But well, I prefer not to have math. It's something that as a kid, I would not like to deal with tensors and algebra. Okay, I just like the idea of physics and all this cool stuff happening, but eventually you'll have to do math if you're really serious about physics. So if you really like that math, yeah, you like physics, you have to do math eventually. And I think it is what opens you to a whole new world of possibilities and horizons if you really want to study physics. Okay, so let's start with picture. The usual picture, okay, of a neutron, okay, bombarding a nucleus of uranium-235. Okay, so the way we write, okay, the way we write numbers, okay, okay, it's like so. You might see this uranium-235-92. This is how we usually write elements. Okay. Okay. So we like to call these numbers A and Z. I'm just doing a quick check now to see which is A, which is Z. Okay. So this 92 here is the Z number or proton number. So that's how many protons. Okay, I assume you know some basic atomic physics where an atom is made up of electrons, protons, and neutrons. So this is the total number. We call this A, which is a total number of neutrons plus protons. Okay, so we call this the so-called A and Z number. So again, the Z is what we call the proton number. A is the total number of neutrons and protons. So this neutron here, we also use this notation to write a 1 0, 1 for one neutron, 0 for no protons. So this is the way we write in nuclear reactions. Okay, so the picture is a neutron will go into uranium-235, and this thing will so-called undergo fission. Okay, you undergo fission into two fragments, and maybe 2 or 3 neutrons will come out. So this is a fission process. So this is a greatly, again, simplified way. There's a little bit more nuance to go to what's going on here, but this is the basic idea. Okay, so this is what makes nuclear reactions work. Okay, you don't only have uranium-235, you can have uranium-233, and plutonium-239. All of these can go this sort, yeah, this sort of fission reaction. This sort of fission reaction. Now, you might be asking, why doesn't this happen with anything else? Let's say uranium-238. Okay, sometimes we may not write out the full way, like uranium-23592. We just use a shorthand method like uranium-238. Okay, this is a shorthand method because we kind of know uranium already has 92 protons. Okay, so you have this uranium plus neutron. Okay, why doesn't it always split? Okay, it doesn't always split. It becomes uranium-239, and sometime later it will become plutonium-239. Right? So this is these are some things that nuclear physics will help us to, sort of wrap our minds around. Okay, it's a bit of a complicated process because I have to explain quite a fair bit to get you to this point as to why sometimes you smash a neutron into this uranium-235, it splits, smash it into this uranium-238, it doesn't split. It will just absorb the neutron and then suddenly becomes plutonium-239 after some time. Why is that? Okay, so to delve into that, we need to understand a little bit of quantum physics. So I know the word quantum physics will sort of already make a lot of people's minds switch off. Okay, because it sounds complicated. The person who doesn't study physics or any of these will find this really complicated. So again, I want to do away with the math. I want to do away with the complex stuff, and I try to introduce quantum physics in as simple a way as possible so that, hopefully we can begin to understand the physics behind a fission process. Okay, quantum physics. Okay, the key idea of quantum physics, at least for me, okay, key idea of quantum physics is that okay, the key idea of quantum physics that separates it from all other physics, or what we call classical mechanics, where we have Newton's three laws and all that. Quantum physics wasn't around till the 20th century. It wasn't seriously studied until the 20th century. This most of the important developments for quantum physics and nuclear physics was done in the 20th century. Okay, key idea of quantum physics. Okay, you can say matter here. Matter, that means protons, neutrons, and electrons. Okay, protons, neutrons, and electrons. So I do a proton here. Okay, never mind. I'm not going to draw it. Protons, neutrons, and electrons. Okay, they can behave as a particle. That means well, I can put it like billiard balls, golf balls, ping pong balls, all of these are a very good picture of what particles are like. Okay, but at other times they also behave as waves. Okay, okay, that's the basic idea of quantum physics. Okay, particles, I mean matter, protons, neutrons, and electrons, they can behave like particles, or they can behave like waves. So sometimes they behave like particles more, okay, but as soon as you so-called observe them, okay, I mean, sometimes it behaves like waves. Pardon me. Sometimes they behave like waves, and then the moment you observe them, they start behaving like particles. This is a really weird fact of life. Okay, why it happens, I am not 100% sure. It's just something we live with. It's just the reality. I take engineering, so all these physics concepts is that I see something work a certain way. Maybe my job now is not to ask so much why. It's like what but my job is to see what can I do with it. How can I make it useful for people around? Okay, to make something practical. Okay, so that's the job of the engineer. It makes something practical of these physical processes. Hopefully, for engineering is profit, or maybe to make someone's life better. Okay, so that's the whole idea. Okay, so where this is seen is what we call the famous uh, Young's double slit experiment. Okay, so what this guy called Young did, okay, I'm going to maybe use orange. Okay, is that he fired particles through a slit. Okay, he fired particles through a slit. All right, and what he observed is that even if he fired neutrons or protons maybe or some others, these are normally things that happen with matter. What he observed was that he saw an interference pattern on this side. Okay, so what is this interference pattern and how does it work? Okay, interference pattern. Okay, so this interference pattern happens with light. It also happens with protons and electrons. So this is something very strange. Okay, and first, light is something we know to be also called EM wave. Light is something we know to be an electromagnetic wave. Okay, so they behave like waves. Okay, and they make this so-called interference pattern. Okay, why does this interference pattern become evidence of wave behavior? So let's start with something we like to call. Okay, I'm going a little bit deeper into concepts now. Going into this concept of waves and superposition. What is superposition? Okay, a lot of new terms for you. Superposition, waves and superposition. Okay, so superposition is basically this idea. Let's say you have a wave that is traveling like that. Okay, it can be a water wave, it can be a sound wave, it can be any sort of wave, even a light will do. So let's say you have a wave like this hum that is traveling at t equals 0, and it's traveling to the right, like so. So it's maybe t equals 1. So the wave is traveling to the right. Okay, the wave is traveling to the right. Okay, and then you have wave number 2. Let's say let's use black. So t equals to 0. You have a wave right here. And after some time, maybe t equals to 1. Wave is traveling to the left. Okay, so here's the picture. The wave is traveling to the left. Now let's say these two waves meet. So I'm going to draw it like that. Okay. And then we will have the so-called black wave. Okay. So let's call this t equals to 0. And after some time, they sort of meet. T equals to 2.5. I'm just making up numbers, so don't mind me. Okay. Okay, so here's where just before they meet, Okay, so the black wave is traveling left, the blue wave is traveling right. And after some time, they will meet up and they will form a bigger wave. Okay, they will form a bigger wave. So you can say that this big wave is the contribution. Big wave is contribution, or rather the sum of the two smaller waves. So that's the basic idea of superposition. Okay, this is basic idea of superposition. Okay, the two big waves become the sum. Two small waves, they contribute to become one bigger wave. Now, not all superposition is like that. Okay. Sometimes you have, let's say, this black wave. It is a wave that is so-called downwards. Okay, there is some negative, what we call amplitude. Okay, so instead of the wave going upwards, the wave is like going downwards, and it's so-called traveling to the left, and the blue wave is like this, traveling to the right. So, and then what you have is that after some time, they are about to meet. Okay, and then what happens? If they are equal in so-called size, or what we call amplitude, if they are equal in amplitude, you sort of cancel each other out. Okay, if they are equal in amplitude, they cancel each other out. Well, alternatively, if they are not equal in amplitude, let's say the blue wave is bigger. If the blue wave is bigger, then what happens is that you have a really small hump. Okay, if the blue wave is bigger, you have a really small hump. Okay? If the blue wave is bigger than the black wave, you have a really small positive hump. But they sort of cancel each other out too. Okay, they sort of cancel each other out, but not completely. Okay, so that's the same idea of superposition, that this small wave or this cancelling out effect is the sum of the two contributing waves. So there's a wave over here on the left that's blue, a wave over here on the right that is black. And when they meet together, they either build on each other or they cancel each other out. Now, this is what we call superposition. And we have a special name for when the waves build on each other. Okay, when the waves build on each other, okay, when waves build each other, when they build on each other, we call this constructive interference. Okay, when waves build on each other, we call this constructive interference. When waves cancel each other out, we call this destructive interference. Yeah, I might not be spelling anything of this right, but don't mind me. So this interference pattern is an alternating constructive and destructive interference. Okay, so how does this happen? Okay, how does this happen? So let me go back. So how does this happen? Okay, so let's say you have a water wave, right? A water wave that is circular and is traveling towards a wall with two slits. Okay, we call this a double slit. Okay, I'm not going to be too technical or too strict, but I just want to give you the basic idea. Okay, if you have a water wave that's traveling towards this slit, and so this is a circular water wave and it's positioned like in a special way. I'm not going to say what way, but you kind of position it behind the slit. And the water waves, if you actually take a look at the cross section, it's something like this. We like to call this a sine wave. Okay, but it could be a sine wave, it could be some other mathematical function, but we normally like to start with sine waves. Okay, so basically, you have one peak. Okay, I think we call it the crest, and this low point is what we call the trough. Okay, oops, crest and trough. I'm just searching whether I get it right. Yeah, so the highest part of the wave is called the crest. The lowest part is called the trough. I just dropped my pen. Sorry. So we have this sort of idea here. We have a crest and trough. Okay, and then when it hits, this is the cross section of the wave. So when the wave actually hits the double slits, you actually form another two sets of waves. Okay, two sets of waves. Okay, you have one here, which I will call orange, the orange wave. Apologies if you're colorblind, but the one at the bottom is slightly different. Maybe let me use a different color to make it a little bit more obvious if you are looking at this in grayscale. Okay, so there are two sets of waves. Okay, two sets of waves. Two sets of waves. Okay, and when these waves they kind of go out radially, they will start to crisscross each other. Okay, they'll start to crisscross each other. For example, at this point, okay, so the idea is that as the waves go out, they sort of crisscross each other more and more because they are expanding radially. Okay. Yeah, my drawing is kind of horrible, but do pardon me. But you see, there are more and more points where they start crisscrossing each other. So I'm just going to highlight these. Okay, maybe here they crisscross here, they crisscross here. Okay, so if let's say these bends represent the crest, if the bends represent the crest, then these black dots are when the crests meet. That means the top part of the crest of the top wave will also meet the crest of this bottom wave. So when you have two crests meeting together, that means it's this part, two crests meeting together, they will have this constructive interference. Okay, so they will have this constructive interference pattern. Okay, but when the crest of this green wave, okay, maybe the trough of the orange wave is somewhere here. The trough of the orange wave, which is the low point, when the crest of the green wave meets the trough of the orange wave, we have what we call destructive interference. Okay, we have what we call destructive interference. So let's say we have this and then we go towards a wall. Okay, and what we will see is that there will be a pattern. Okay, because there's some constructive interference here, then there's a destructive interference here, there's constructive interference here again, and that is what will give you so-called interference pattern. That looks something like this. I may be wrong as to the specifics, but this is the basic idea. Now, of course, you can have more than two slits, you can have multiple slits, and that's what we kind of study in diffraction grating. I kind of forgot a lot of my old physics concepts, but this is the basic idea. this interference pattern gives evidence that whatever you're putting through this double slit behaves like a wave. Now, okay, so I will stop here. Maybe next time I'll talk more and continue on to this wave particle thing and how it correlates to nuclear physics. But for now, I'll stop and maybe take a little break. I'll see you next time.